Good afternoon, I am Ariff bin Hakimi and I will be presenting my literature review titled Mammary Lactogenesis Mechanism, Factors and Effects Towards Human Milk Long-Chain Polyunsaturated Fatty Acids. Human milk is considered the gold standard for infant nutrition. It not only provides essential calories but also contains a rich array of bioactive compounds that support immunity and development. Of particular interest are long-chain polyunsaturated fatty acids or Lc-Pufas, especially docosahexaenoic acid (DHA) and arachidonic acid (ARA), which are vital for brain, retinal, and immune system development in infants. The process of milk production is known as lactogenesis, which occurs in two stages: secondary initiation before birth and secondary activation shortly after delivery. Within this process, the mammary gland performs de novo lipogenesis or DNL to synthesize fatty acids that make up a significant portion of human milk fat. Although Lc-Pufas like DHA and ARA are crucial, they are not synthesized directly by the mammary gland. Instead, their incorporation into milk depends on maternal diet intake, liver lipid metabolism, and biochemical environment created by mammary DNL activity. This means that the way a mother's body processes fat and carbohydrates, along with her nutritional and hormonal status, can greatly influence the availability of these key fatty acids in her milk. Understanding these interactions is essential for optimizing infant nutrition during the critical early stages of life. The concentration and quality of Lc-Pufas in human milk play a major role in promoting healthy infant neurodevelopment and immune function. However, these fatty acids are not synthesized within the mammary gland itself. Their presence in milk depends on external factors such as maternal metabolism, diet, and the mammary gland's DNL activity. There is currently a knowledge gap regarding how DNL mechanisms and maternal metabolic states, such as gestational diabetes mellitus and obesity, affect the incorporation of Lc-Pufas into milk. This gap becomes even more relevant as maternal metabolic disorders are increasing prevalent. Therefore, this study aims to explore and synthesize current literature to better understand these mechanisms and support improved maternal dietary and lactation strategies. The objectives of this critical review are: first, to examine the mechanism of mammary de novo lipogenesis and its role in synthesizing milk fat. Second, to identify the biological, hormonal, and dietary factors that regulate DNL activity. Third, to explore how abnormalities in DNL affect the levels of DHA and ARA in human milk. Fourth, to assess how these changes impact both maternal lactation success and infant development. And finally, to evaluate how modern metabolomic profiling technique can detect and quantify Lc-Pufas, providing better insight into milk quality. Lactogenesis occurs in two stages. Lactogenesis 1 begins in late pregnancy and involves breast tissue differentiation. By this, the breast enlarges. Lactogenesis 2 starts 2-3 days after birth and marks the onset of copious milk secretion. These processes are hormonally driven, involving prolactin, insulin, cortisol, estrogen, and progesterone. Together, these hormones regulate mammary gland development, milk fat synthesis, and nutrient transfer to the infant. Mammary DNL primarily synthesizes short and medium-chain fatty acids using substrates like glucose and acetate. These fatty acids act as scaffolds or vehicles for integrating long-chain fatty acids like DHA and ARA into milk fat globules. The enzymatic pathway responsible for elongating and desaturating fatty acids include FAA, FASN, ACC, ELOVLV5, and FADS1-2. While the mammary gland does not make DHA or ARA, it plays a major role to their delivery by providing the lipid matrix into which these fatty acids are inserted. Several key factors influence DNL. Hormones like prolactin, insulin, and cortisol stimulate or inhibit the expression of lipogenic enzymes. From a dietary perspective, high carbohydrate intake promotes DNL, while omega-3 and omega-6 intake influence Lc-Pufa composition. Maternal metabolic health also plays a role. Conditions like gestational diabetes and obesity impair desaturase activity, potentially lowering DHA levels in milk and affecting infant health outcomes. When DNL activity is disrupted, it can result in reduced DHA and ARA levels in milk. In infants, this may lead to developmental delays, impaired cognition, and weakened immunity. For mothers, abnormal DNL is linked to lactation difficulties, increased risk of matrices, and heightened emotional stress. DNL abnormalities affect maternal lactation success rate, post-spectrum health and emotional well-being, as mothers may feel frustrated and emotionally distressed when the milk supply is low or milk composition is inadequate. In the long term, poor milk lipid quality may contribute to higher risk of obesity and metabolic disorders in children. Mammary de novo lipogenesis, or DNL, plays a foundational role in synthesizing the short and medium chain fatty acids that form the structural base of human milk fat. These fatty acids make up the lipid matrix that supports the incorporation of long chain PUFAs like DHA and ARA. While DNL doesn't directly produce DHA or ARA, it creates the environment needed for their transport and stabilization within milk fat globules. Therefore, understanding how DNL works helps explain how milk fat is structured and why it's essential for delivering this critical nutrition to infants. DNL activity is regulated by a combination of biological, hormonal, and nutritional signals. Hormones such as prolactin, insulin, and cortisol influence the expression of lipogenic enzymes, especially during the transition into active lactation. Diet also plays a role. High carbohydrate intake stimulates DNL, while the balance of omega-3 and omega-6 fatty acids can alter the overall milk fat profile. At the molecular level, transcription factors like SREBP1C and PPARY are key regulators of lipid metabolism in the mammary gland. These elements help explain inter-individual differences in milk composition and provide targets for dietary and therapeutic intervention. Impaired mammary de novo lipogenesis, or DNL, can negatively affect both maternal and infant's health. Reduced DNL lowers milk fat content and disrupts the incorporation of DHA and ARA, fatty acids essential for infant brain development, immunity, and growth. Metabolic conditions like gestational diabetes and obesity impair desaturase enzymes, leading to lower DHA and ARA levels in milk. This may result in delayed neurodevelopment and increased risk of metabolic issue in infants. For mothers, poor DNL function can reduce milk supply and trigger emotional stress, especially when feeding challenges arise. Overall, maternal metabolic health is closely linked to milk quality and infant's outcome. Specific metabolites produced by DNL, such as palmitic acid or malonyl CoA, can influence how well Lc-Pufas are integrated into milk lipids. To detect and study these processes, researchers use advanced metabolomic profiling tools like UPLC-MSMS mass spectrometry, which allow precise quantification of individual fatty acids. These techniques reveal correlation between milk composition and maternal metabolomic health and help identify biomarkers of milk quality. Ultimately, this supports precision nutrition strategies that can be tailored to both maternal needs and infant developmental demands. Lc-Pufas are like DHA and ARA are essential for synaptogenesis, myelination, and immune function during early development. When their levels are low in breast milk, infants are at a greater risk of poor cognitive outcomes, weaker immune response, and delayed visual development. Moreover, altered milk lipid profiles may also signal maternal metabolic stress, which can impair lactation success and recovery. These findings highlight the clinical importance of monitoring milk fat quality, not only to support infant development, but also to reflect and improve maternal health.